Yeah, I think I had a harder time with part B of this. Just it's one of the ones where you kind of need to go ahead and explain like, hey, why does this make sense? And I'm just having a harder time with like, yeah, I'm just not that familiar with it. So
All right, good. Okay, let me share my screen here. Oh, I probably should have rebooted stuff over the break because there was a couple times
just
it froze.
yeah.
We'll see where this gets us. All right, so chapter 19, number 34. All right, let me go to your class and the questions. Number 34. Oh, okay. So 34 says a liquid with a coefficient of volume expansion beta just fills a spherical volume of VI at a temperature of TI. See figure 33 above. Okay. The shell is made of a material that has an average coefficient, a linear expansion of alpha. Okay. The liquid is free to expand up a capillary area A, projecting from the top of the sphere. A. Assume that the temperature increases by delta T. Show that the liquid rises up the capillary by an amount, delta H, given by this equation. Okay. So the idea here is, of course, thermal expansion. And so if you have something, in this case, it's really two things. I'll try to label it or show it with an outside perimeter here. But there is a container, and in fact, they don't say what the material is, but this looks like a good example of a mercury thermometer, where we have mercury here as a liquid on the inside, surrounded by glass. And so when you warm it up, you're going to get an expansion due to the liquid, but you're also going to get an expansion to the container itself. And the question of how much does it go up may be a question of it doesn't go up at all if, say the glass surrounding the mercury expanded enough that it was the same as or even bigger than the expansion of the mercury. So mercury and glass are typically used for thermometers because glass does not change by much, and mercury changes by a lot. So you can roughly say, don't worry about the container getting bigger. But this problem wants us to worry about both here. So let me do this. Let me I keep saying mercury, but that's really not the problem. There's a liquid on the inside. So let me call that material 1. And then the material on the outside is the container. Let me call that material 2. So I guess I would do something like this, that the change in the volume of number 1, the liquid that's inside, would be beta times the initial volume times delta T. So that's our equation for our volume expansion. And for liquids, that's all we ever have. Now, for solids, and I'm going to take the outside container to be a solid, we have, and maybe I'll just put it over here. We're not going to need the length, but the change in length is this alpha, that's why it's called the linear expansion, times the initial length, delta T. And if you have a container, it's going to have a length, a width, and a depth to it. So the change in volume of number 2 being the solid material, the volume expansion is going to be 3 times the linear expansion. And maybe I'll just pause right there. I don't know if you got that out of the videos or the reading, but when you have a solid object, you could talk about how much does it expand in length, how much does it expand on surface area, or how much does it expand in volume. And so since the volume is length times width times volume, it turns out that the volume expansion of a solid is 3 times the linear expansion. So, yeah, so it sounds like that might be kind of new to you.
Yeah, that makes it actually a little bit more sense, because our volume is like whatever that unit is cubed, so we're scaling it up a lot.
Right,
Yeah.
right.
Cool.
Hey, you could actually see it in something like this. If I go, length times width times height, there's going to be, for each factor, there's going to be the original plus an alpha delta t. And so when you go to do a volume, you have that cubed. And when you do a binary expansion on it, you get 1 plus 3 alpha delta t. And then I guess technically it's 3. No, wait. It would be. Yeah. 3 times length times width. Yeah. Well, and then there'd be higher order powers. I was trying to do that in my head and I can't. But if you just multiply it out, then you start getting things like squared and cubes, and all these are kind of small. So anyways, that's our argument, that it would just come out to be 3 times the alpha t. Okay, so that's the key to this problem. And that's why also in the book, and both books, you'll never see them list a volume expansion for a solid. It'll always be a linear expansion, knowing that, hey, if you're talking about a volume, just multiply by 3. If you're talking about an area, multiply by 2. Okay, whereas a liquid only expands in terms of volume. It makes no sense to talk about a linear expansion. It's kind of a, it flows. That's why it's called a liquid. And so it just, yeah, so there's only a volume expansion. Okay, so if we take volume number 1 to be the increase of the liquid, but if we subtract off the increase of the container, the difference between those is how much actually goes up the capillary tube. Okay, so that's so in other words, if the liquid expands more than the container, then the extra more than the container is what goes up. If they expand the same amount, that number is 0 and nothing goes up the container. All right, so that difference between those two is what goes up this capillary tube. Now, the volume then would be in this little cylinder here. And so this extra volume would look something like this if it has a cross-sectional area of A and a height of what they call delta H. Then I would have area times delta H for that volume. So that's where it's all going to go. It's going to go up that little cylinder. So now I can put these together. So this would be beta times initial volume delta T minus 3 alpha initial volume delta T equals to the cross-sectional area of the capillary tube times delta H. And I think this problem said solve for delta H, assuming that the temperature increases by delta T, show that the liquid rise up the capillary tube, delta H is given by, all right, so let's see what I have here. So I would have a beta minus the 3 alpha, and then the initial volume and the delta T, all divided by the area. And I think that's what they have. There's the beta, initial volume, delta T over the area. Yep, there it is. And if you ever work a lot with thermometers, you'll notice a pattern here, especially thermometers that you want to be accurate and have, maybe you want to read it not to the nearest degree, but a tenth of a degree or even a hundredth of a degree. They tend to have either really narrow capillary tubes, A is small, or the volume of the bulb down at the bottom is really big. And so we got some pretty accurate thermometers in the lab, and the bulb of mercury is really long. It's like an inch long. It's huge, and there's, I think, 20 marks between each degree, so you can read it to a 20th of a degree. So
Wait, so those have a bigger bulb, but like just a standard capillary size? The ones that you're talking about right now?
yeah.
Mm.
So the ones
Okay.
I'm talking about, so kind of our standard ones look like this. They've got a glass tube, and they've got a bulb in them that's maybe about that big compared to our other ones that got a huge amount of mercury in them. And then it just goes up so much higher that it's got to be much longer.
Mm-hmm.
If you're talking about the same temperature range, maybe 0 to 100. 0 to 100.
Oh, and that would just make it more accurate there too, because you could go ahead and have smaller values in between. Mm-hmm.
Right. So the standard ones, you can just read every degree, but these, there's little tiny marks, and then you get to 1 degree. So there's 20 marks between each degree. So you can read it to a 20th of a degree. Now, like I said, they can do the same thing with a smaller capillary tube, but at some point you get the capillary effect from the capillary tube. So you don't want to go too narrow on that one. And the other thing, like any thermometer, you can kind of see that the higher it would go up, the bigger the temperature change. So, that's your standard thermometer. If delta T is 1 compared to 10 or compared to 100, it goes up much higher for 100 than 1.
Since we're on the topic of it, just for thermometers, do they have to deal with issues with like meniscuses in like graduated cylinders? I know when you're dealing with some liquids in like chemistry or whatever, like you don't get accurate readings in that because you actually have like a dip in the liquid where the surface tension grabs the walls of the vial. Does that happen with those, or is that just no?
You do, but it's so small.
Mm-hmm. Okay.
That you don't really see it. Yeah.
Cool. I was just curious because I'm like, hey, we're already on it, so.
Yeah. Your graduated cylinders, and mercury's actually kind of the opposite. The graduated cylinder, the water clings to the side and goes like that. So you want to take an accurate reading, you want the bottom of the meniscus. If you were to fill it with mercury, it's the reverse. Mercury does not like glass at all. And so the meniscus looks like this. So you read it kind of like that. Yeah.
And then I'm guessing for part B there, we basically just kind of answered the question about like why a mercury thermometer would be good for the a good approximation if you're trying to ignore the shell expansion, and that's because mercury is like really reactive to temperature change compared to most others.
Yeah. For a typical system such as a mercury thermometer, why is it a good approximation to ignore the expansion of the shell? And in fact, I'll use this as chance to go back to the book like we were doing before the break, and I'll just look up the beta for mercury. We're looking at 1.82 times 10 to the minus 4. And for glass, I'll look up the alpha and multiply by 3. Let's see, glass, depending on what kind we use. Let's do how it Pyrex here. It's about a 3.2. So if I multiply that by 3, we're looking at roughly 10. So this is 10 times 10 to the minus 6. Let me just call that 10 to the minus 5. But so this is 1 times 10 to the minus 5. I could write this as 18.2 times 10 to the minus 5. So the mercury expands 18.2 times more than the glass. So does it have a little effect? Sure, but mercury is, again, 18 times more is huge. So, yeah. In fact, it's if you're real careful with a mercury thermometer, it's kind of interesting. You can take the mercury thermometer and put it like in hot water and just kind of put it down into the hot water. And especially if you have one of these bigger ones I was talking about, because the glass warms up first, you'll actually see the mercury drop a hair. Yeah, because the container holding the mercury gets bigger without the mercury getting bigger at first. Of course, then it warms up the mercury, so then the mercury starts to rise. But you put it in, and if you watch that mercury, it looks something, like this. You put it in, and the mercury goes down, and then it goes way up. You put it in hot water. So.
Sounds like a lot of fun. Too bad I shouldn't be playing with mercury at home.
Yeah, and yeah, we're one of the few labs that still have our mercury thermometers around. In theory, you should see the same thing with an alcohol thermometer. I should try those. But again, the kind of ones that, like I'm saying, the ones we put out in the lab are the simple ones anyways. I'm not sure how much it would be noticeable with that one. You got to get to our more accurate ones, which
Cool. Awesome.
Keep around.
Thank you.
Mm-hmm.
Okay, I have a question if you have a time right now.
Yeah. Either ask it now or throw it in the chat, whatever you like. Let me come back to my.
I already did my lab, my vectors lab. I just want to know if I'm doing this right. I did 5 drawings, and the only page that we have to submit beside the 5 drawings is only 1 page, correct?
You should turn in your drawings.
5 drawings.
5 drawings, and then I think the only other thing.
This guy.
Yes, that one.
Okay.
Yeah. And that one. That one should have drawings. You should have data on top, and then 3 questions on the bottom.
Yes, correct. Some drawings were accurate, and one was a little bit off. I did it 3 times. It was very hard. I think it's the drawing number 4. That was very hard to do. And but yeah, the measurements were kind of accurate. I got a good protractor, and I got paper and everything. So
good.
So I think that's gonna be all for this lab, huh? Yeah. And when are we having our first exam?
So your first exam is on the 11th, which would be Thursday, 6 days.
And how is gonna be like?
Yeah, good point. Let me explain the test, but I'll write this out on the coming up here on the weekly announcement Sunday tomorrow, or maybe I should even do that tomorrow so you guys have it a little earlier. But the test is a lot like your homework, where the first half are multiple choice questions. Okay, where there'll be a little more conceptual questions than the long calculation ones.
Okay.
And there'll be 4 from each chapter.
Okay.
Okay. Then there will be 2 from each chapter of calculated problems. I call those free response.
Okay.
Where they look hopefully like the homework, where you just write in, like it says, how far did the ball fall after 2 seconds?
All right.
And then you just show your work and then box it. And that again would be 2 from each chapter.
Okay.
Well, I should say, not counting the first chapter, because the first chapter didn't really have any calculational problems.
But my main question is how we're gonna do it. You're gonna give us the test, so
Yeah.
we're gonna do it, and then we're gonna scan it and send it to you.
Right.
How long is gonna be that? How long is gonna be give us for the test? How long is gonna be?
Okay. Let me think this through. You get like a regular class time, so you get an hour and 20 minutes for the test. Plus, I like to just throw in an extra 25 minutes for scanning it and uploading it and all this, stuff that you got to do, rather, beyond just, in a class setting, you would just get up from your desk and hand it to me. And so now you got to scan it and turn it in. And so I give an extra 25 minutes for that.
Okay. Don't you think for scanning that's kind of short time?
Short time?
because sometimes things happen, like the internet is down and
yeah. Okay. If you have any problem, and so I'll be available. Just to shoot me an email. During test time, I'm just going to sit right there in front of my computer, and if you have any questions, just shoot me it. And at the end of the test, if you have any internet problem, just let me know.
So you're gonna email us the test on how it's gonna work, or you're gonna upload the test in Canvas?
I'm gonna load the test in Canvas. Okay. And in fact, when I send out this information Sunday, I will ask everybody to go to Canvas and click on exam number 1, and so you'll see what you're looking at.
All right.
And if you, in fact, if you did it right now on Canvas, I think you would see it there, and you'll see it says locked. And it says you can't view it until 12:45 on Thursday the 11th.
Okay. So once we unlock it, and then we do it, and then we send it, correct?
You either scan it or take a picture of it and put it back onto Canvas. When you click on it, like your homework, it says it says upload file.
Okay. Yes. Okay.
Yeah. Like you did in your lab, like you're about to do. Think of your lab like you just did the test. Okay.
All right.
So you do the test with pencil and paper, and now you're all done, and you got those pages there. Now you're going to scan it and turn it in on Canvas.
Right. Okay. Yeah. Sounds good. So then I let you go with I have to do so. I have so much homework to do. Okay. So bye. Thank you.
Okay. Bye now. Good talking to you.
Yeah.
Yes, I need to make sure I get 102 people going and feel comfortable about how do you do these weird exams online here. All right, well, I'll take this one off. Look in the chat here. I don't see another question in the chat. I don't know if do you guys have another one for me, or I should pause till you do, or what?
Yeah, I'll go ahead and I'll send another one in there.
Okay.
This one is one about a hot air balloon, and that one's just a little weird.
Okay. Yes, I remember the hot air balloon. It's also going to require us to go back to Physics 121 a little bit. Let's see, what time is it here? 1:05. Chapter 19. Do you remember what number that was, or do I need to find it here?
It's number 21.
21, okay.
Yeah.
All right, let's try that one here. All right, so chapter 19, number 21. Okay. So let me read it here. It says the mass of a hot air balloon and its cargo, but not including the air inside the balloon, is 200 kilograms. The air outside is at 10 degrees Celsius and at 101 kilopascals. The volume of the balloon is 400 cubic meters. To what temperature must the air in the balloon be warmed before the balloon will lift off? The air density at 10 degrees Celsius is 1.25 kilograms per cubic meter. Okay, so thinking of hot air balloons and maybe drawing them, I guess they look something like this. They've got a big opening here. Kind of look like a Niemeyer flask upside down. Of course, they have a basket hanging underneath it and a big old flame here making it hot inside. Okay. That's a terrible looking balloon. But okay, so there's my hot air balloon. And going back to physics 121, if I look at the sum of the forces, there is gravity pulling it down, mg. And what lifts a balloon up is called the buoyancy of it, the buoyant force. So this is our chapter 14. It's Archimedes' principle. Archimedes' principle says the buoyant force is equal to the weight of the fluid. And in this case, our fluid is air. So it's the weight of the air that's displaced. But let me just write that as Newton's second law. All right. So we got gravity pulling down and we've got buoyant force pulling up. Now, for it to just take off, I'm going to put a 0 there for the acceleration. So in other words, when the buoyant force exactly equals the weight, or what's sometimes referred to as a neutral buoyancy, we've got just enough buoyancy to lift us up. Anymore, we will begin to accelerate. And so just to be uncautious, with the balloon, you don't want an acceleration. You want your acceleration to 0. Maybe a little bit to get you going at first, but once you start rising, you just want to keep it at that same speed. So, you're going up about 1 or 2 meters a second and you're going up. You don't want to be accelerating as you go up. Okay. So that's why I'm going to set the acceleration equals to 0. And so what that means is I'm looking for when the buoyant force is equal to the weight. Okay, now, here's what's interesting about a hot air balloon. When you get started, it doesn't rise. Or put another way, the weight is more than the buoyant force. So in order to get them equal, you have to either A, increase the buoyant force, or B, decrease the weight. And the way a hot air balloon is it decreases the weight. Now, you may argue at first if the balloon gets bigger, but a hot air balloon is not like a helium balloon where you blow up and it elastically gets bigger. You may or may not know that. But a hot air balloon is just material, and it fills up that material. And once you get that balloon to that size, its size doesn't change. That's as big as it gets. So it displaces a certain amount of air that would have been there, and it never gets more or less once I fill up the balloon. So granted, I got to fill up the balloon first. So there's only the hot air balloon is barely hot when it gets full, but then I start getting it hotter and hotter and hotter. And what's happening is by getting it hotter, I'm actually chasing air molecules out of the balloon. And again, unlike a helium balloon, it's not tied at the end. It doesn't have a fixed amount of molecules contained inside. The idea of the hot air is to chase molecules out. And so what I'm trying to say is we end up lowering the weight of the balloon until it equals the buoyant force. We don't increase the buoyant force until it equals the weight. And so that's, I guess, one thing that needs to be understood about a hot air balloon that may not be common knowledge. So I'm glad you asked.
I had no idea. Yeah, I had no idea. That's one of the things I was confused about, is trying to figure out, Mike, where do you go from there in terms of consumption of big.
Okay, good. So I'm glad I spent some time on that, because working with students in the past, I know they've struggled with that because their mental picture is an old-fashioned, or not old-fashioned, but just a regular balloon where you keep blowing it up and you put more and more molecules in it, and it gets bigger and bigger, and that's not how a hot air balloon works. Okay, so with that in mind, here's what I'm going to do next. All right, so for the left-hand side, again, going back to physics 121, the buoyant force is equal to the weight of the displaced fluid. So I'm going to put over here mg, but underneath this m, I'm going to put displaced air, because the buoyant force is equal then to whatever the weight of the air that would have been there if it wasn't for the hot air balloon. Okay. Now, I wanted to put that under here because I didn't want you to confuse that with the mass on the other side. Remember, this mass was the mass of this whole hot air balloon. That's actually the weight of the balloon. So this m is actually the, maybe I shouldn't put hot, I'll just put balloon. And in fact, now I'm going to do another step, and I'm going to put m plus m times g. Because the hot air balloon can be described as two different masses. The mass of, I'll call it the payload, everything you're trying to lift up, the basket. Let's just say this is a recreational hot air balloon. So, we've got a basket and a pilot and a couple on their romantic Valentine's sunset hot air balloon ride. Okay. So all of that stuff, they say, what did it say here? The mass of the balloon and its cargo, but not the air inside, is 200. So for the moment, I'll just put cargo, because that we can't change. We can't lower the mass of the cargo. Actually, well, hot air balloons sometimes are kind of tricky. They tie sandbags on the side so you can cut them off and change it. It's a one-time thing. They fall to the ground.
Isn't that a hazard?
Well, yeah. And I'm thinking old school. I don't know if they do that anymore, because it could be a hazard for somebody on the ground.
Mm-hmm.
But then there's also these hot air balloons. I've never done one because they're a little pricey, but I've always wanted to. They do them in areas where it's, well, number one, you have to get allowed by the local area. And number two, it's often places that, have a lot of open space. One that comes to my mind is I've seen them in Lake Havasu. You launch from the river, and all you do is you float out over the desert. So there's nothing to drop in on, but yeah.
Yeah, what's the harm in putting more sand there?
Yeah, they probably where they got the sand, right? Anyways, but this problem doesn't seem to have that. We're not going to change the mass of the cargo. So keep in mind that that's 200. But now here I'm going to put the mass of the hot air. And this is the stuff that's actually in the balloon. And my concern is you might confuse the mass of the two airs. So I'll say it again. This one here, the hot air, this is actually the air that's in the balloon. This one over here on the left is the air that would have been there if the balloon wasn't there. So it's cold air, basically.
Question. So does just because like conceptually on this, so the mass of our buoyancy on the other hand is the air that would have been there but that has been displaced or whatever.
Right.
Does that mass change as you continue to float the balloon, or is that just a constant mass there? Like,
Well, it depends on the density of the air. So in a real world problem, it would change.
mhm.
In this problem, no, it doesn't change. They just say take the air density on the outside to remain at 10 degrees and be 1.25 kilograms.
Okay, cool.
And for a recreational balloon that only goes a couple 100 feet up, that's probably pretty true.
Mhm.
For a weather balloon, no, not true at all.
Mhm.
The density changes dramatically.
Okay.
And for that matter, a weather balloon, the volume, it's a different game. They actually have this big weather balloons when they launched look like this. They look like a plastic bag that is barely full.
Mhm.
And because as the pressure gets lower, the gas inside, it's not hot air, it's helium, gets bigger and bigger and bigger and bigger and bigger because of the lower pressure. So you
And those are
displace
tied off, right?
Huh?
Weather balloons are tied off though, right? They're a closed
Yeah.
container.
Yeah,
Okay.
so they're tied off, yeah.
Hmm.
So yeah, but as a result of that, you can get these weather balloons to be, 150,000 feet up. I mean, there's amazing how high you can get them. Okay, but that would be a fun discussion about weather balloons too, and that kind of thing. And in fact, I don't know if you're familiar with the whole Roswell, New Mexico, and the aliens of 1951.
I've heard a couple of those things before. I know that if I'm not mistaken, a lot of those were like mistaken as weather balloons there too.
Yeah. So there was a big one in 1951 that kind of kicked it off. And it wasn't a weather balloon. It was actually the Air Force set up, discovered that high up in the atmosphere, sound waves were trapped. And so when the Russians would test atomic weapons, the sound would get trapped up there and it would echo around the world. So in order to kind of figure out what the Russians were doing, the Air Force would launch these balloons up to the 200,000 foot mark and have very sensitive sound recordings there. And they could actually then be spying on the Russians, but yet they were over American territory. And one of these weather balloons crashed just outside of Roswell, New Mexico. It looked kind of alien and foreign, and nobody wanted to admit to it because we didn't want to tip off the Russians that we were listening. And so nobody claimed it. And so they concluded it must be aliens if it didn't belong to anybody.
But we spied on them by listening to bomb sounds from the other side of the world in the atmosphere.
Oh, yeah.
Huh. That's pretty cool.
My grandfather even collected data in Nevada by seismographs, so ground waves. So he had a job I thought would be so cool. He got on his little motorcycle and he would drive he'd be gone for weeks at a time. He'd pack up his motorcycle with gear and drive out on these deserts, and then he'd get out in the middle of nowhere and he would plant Richter scales, seismographs, and then he would have to drive to the next desert location to be a day away. So he'd spend all day on his motorcycle and get to the next one. And he had to have to, and in those days it wasn't electronic.
Mhm.
So he must have done this in about 55, 56, 57. And then maybe into the 60s. But then he would, everything was on the old fashioned, ink on a paper that would scroll through.
Mhm.
So he'd have to go there and take the paper and unwind it and put it in his saddle packs. And he would go day to day like this. So he'd go like from 4 or 5 of them for the day, and then he would ride his motorcycle back and camp each evening, and then ride back to. Are you familiar with Area 51 outside of Las Vegas, Nils Air Force Base? So he'd ride back to Nils Air Force Base and give him the data, and then they would give him, more Richter scales, and so he'd go out to some mountain somewhere and dig a hole and bury it, and yeah. So that's what he did for like 7 years.
Awesome. Just gotta go collect and deliver scribbles on a piece of paper.
Yeah. I was gonna say my family has an interesting history. We all do, but very poor, and he always wanted to go to college, but never could afford it.
Mhm.
So all of his jobs were science related,
Mhm.
but with no formal education. So he was always that kind of that gopher guy.
Mhm.
And his brother, my uncle, yeah, he worked for this Caltech guy. Actually, that's what got him started in this, because the Caltech professor was, and again, this was the 50s, but he was trying to collect evidence of plate tectonics and how the Pacific plate dips under the North America plate. I mean, today we take it for granted, but the Caltech professor was operating on the theory of what today we call the subductive zone. And so if the Pacific plate went down, the earthquakes would go deeper and deeper as you went from coastal California out to Nevada.
Okay.
As the plate dipped down. So my uncle, which would be my grandfather's brother, I guess great uncle, actually was doing the same thing for a Caltech professor, but his seismographs, he had to go across the Sierras. So he would get on the western side of the Sierras and backpack in and put seismographs from the west side to the east side, and he'd come out at Mammoth. And Caltech had a little cabin for him over there. And so he'd come out and camp and get into a cabin and get his gear and then hike back. And the Richter scales were placed. And then they even went further out into the Nevada desert. And they eventually proved that the earthquakes got progressively deeper. And then we're actually able to map out the angle of subduction. And again, my uncle was kind of the same way. My family always wanted to be, I guess they were always wannabe scientists, and nobody could ever go to college. That's why they were finally my generation. They were so insistent that I go to college. You're going to make it. You're going to be the first in our family. You're going to make it. So
That's awesome.
I don't know if I made it, but I'm just a simple teacher.
Hey, I don't know, Mike. You're a good one. No, that's interesting. I remember working on a similar earthquake problem where you go ahead and you try to triangulate like its position in back when we were 21 with that. So that's really cool.
Yeah. Okay, well, sorry for that digression. I was having some
no worries. That was cool.
There. Okay, so back to this problem. So this problem, and it looks like I need to get some more yellow paper. All right. So back to this. Okay, so we were here, and I was trying to point out then that we're trying to then get where these two match. The buoyant force equals the weight, and the weight we broke down into two pieces. And of course, now we can begin to talk about these other pieces. And I'll start by just canceling off a G on each side. Okay. And then I'll just put the equal sign on my next page. But the cargo is something that doesn't change. So that's just a flat 200 for this problem. And over here, let me point at it. But if you look at this and you look at the numbers, and maybe I'll put up here that density is mass divided by volume, that would mean mass is the density times the volume. Okay, so for this problem, this, and again, I'll just call it the cold air, the displaced air, they give us that density. It's 1.25 kilograms per cubic meter. And they also give us the size of the balloon. The balloon is 400. So, oh, that was nice. That comes out to be an even 500. All right, so the balloon is displacing 500 kilograms. And then, of course, maybe I'll just put here the mass of the hot air. And so if I solve this for the mass of the hot air, I get 300 kilograms. So after that thinking, we're kind of done with physics 121, where we've done buoyant forces and net force and all that. We finally conclude that this balloon would begin to float if we make sure that the air inside gets hot enough that it drops down to 300 kilograms. Okay. Now, here's where this semester begins. Let me use the PV equals nRT. Because if I do something like this, if I say, let's look at density, which is mass over volume. And I take this ideal gas law, okay, and I solve it for volume. Maybe I'll do that right here. So volume equals nRT over P. So this is an N, an R, a T, and then over P. And so if I flip this, I get M nRT times P. Now, let me just say this. Okay. That if I call this initial, so initial density, I know. Initial mass, I know. Initial pressure, I know. Initial number of molecules, I guess I can figure out, and initial temperature. Okay. I'm not liking the direction I'm going. I think it's going to take too long. Hang on. All right. Let me do a restart button here. Okay. Let me come back to the ideal gas law. Okay. So I'm gonna write it this way. PV, and let me pause here with the N. Now the N is the number of moles. Okay. So if I take the number of moles and I multiply it by the molar mass, I get the total mass. Okay.
That makes sense. Yep.
And this is kind of a new notation, so I hope I'm not confusing you. So I'll say it again. I'm going to use a capital M for the molar mass, whereas the lower M is the total mass, as I've been using. I just want to make sure you kind of got the clear of the capital M. Okay. Because what I want to do is get rid of the N by saying it's total mass over molar mass. Okay, so I'm going to write this as total mass over molar mass, and then the R, and then the T. Now I kind of want to do what I started to do up here. Let me divide by volume. We'll get rid of it on this side. And see, I would now have the mass per volume, and that's density. So I have pressure equals density times this R times the temperature over the molar mass. Now, here's why I wanted to do that. If I label these as initial, 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 the same would be true at final. So final pressure would be equal to final density times R times final temperature divided by the molar mass.
Okay. Question: is the molar molar mass from the left equation, the initial to the final, is that going to be the same?
Ah, very good, and that's good. Good. Yes, it is. I didn't want to say that too early, and I'm glad you recognized it before I got there. Because here's what I'm trying to get you to see, and this is why that long discussion of the hot air balloon was important, and to understand, because the air in the balloon never changes its pressure. All you do is keep warming it up and you get rid of the molecule. So you change the density. You don't change the pressure. And as you said, you wouldn't change its molar mass. I mean, okay. So in this equation, when I set these two equal to each other, because initial pressure is equal to final pressure, I can then also cross out the molar mass and also cross out the gas constant. And what I'm trying to get at then is the initial density times the initial temperature would be the same as the final density times the final temperature. And that's what this boils down to. I'm trying to justify, why this relationship exists, using the ideal gas law. Okay, so now this is perfect because I know the initial density. They gave me that 1.25. I also know the initial temperature. They gave me that 10 degrees Celsius. Now, let me give you a reminder and anybody else listening to this video later on that this ideal gas law only works when the temperature is in the Kelvin scale. Okay, so they told me it's 10 degrees Celsius. So let me take 10 and add 273. So this is 283. I want to emphasize that. Okay. Now, the other side of the equation is the final density of the air. Well, that's why I needed to do this physics 121 stuff to figure out, okay, what is the mass of that hot air now? So the mass is 300 kilograms and the volume is still 400 cubic meters. So I guess I'm trying to say is I do know the final density.
Just question. So our first density, what are the units on that one?
Oh, so all the densities here would be kilogram per cubic meter, and the temperature would be Kelvin. So over here, this would be 300 kilograms, and this would be cubic meters.
Okay, cool.
So that once kilogram on each side cancels off and cubic meter on each side cancel off, I'm going to be left with units of Kelvin.
Okay, cool.
Yeah,
Thanks.
so now I can grab this calculator here, 1.25 times 283. Then I'm going to divide it by the 0.75 and get about 472 Kelvin. And if I subtract 273, we're looking at about 199 degrees Celsius for the final temperature. And kind of the general rule is if they give you temperatures in Celsius, you should give an answer in the same units as Celsius. So there's nothing wrong with 420 or 472 Kelvin, but it's kind of the unwritten tradition that you give answers in the same units that they gave in the problem.
Fair.
Yeah.
Awesome.
Cool.
Thank you.
Nice.
Yeah, the physics of the hot air balloon, I think, was the hardest part about that.
Okay, good. Yeah, and I'm glad I went over that. And you made me remind myself that has been probably the biggest stumbling block when in the past when I've talked to students. They'll come into my office and go, and they're just completely lost because they're thinking of it as a tide in balloon and the pressure is changing and yeah.
Nice.
All right.
I haven't really gotten. Oh, sorry.
Oh, I was gonna say it doesn't look like there's anybody else. Doesn't surprise me. You guys just got done with the test. And, I did kind of expected to see some 102 people today, but day's not over. So
yeah, I was kind of.
We did have one. Yeah, we did have one a little while ago.
Yeah. Yeah, at this point, I'm like, those are kind of some of the ones that I just like kind of glanced over and started a little bit. But so far, I haven't really given much of a start on any other ones so far.
Totally understandable. I think I joked with you guys last week, but it was a serious joke that, I didn't really expect too many of you because you just took a test. I mean, you were studying physics, which means you probably weren't doing your math or chemistry or something. And so now you got to catch up on those.
Yeah, I'm probably going to be doing that over the last little bit of today too. So,
right.
Yeah. Cool. I'm actually going to get hopping on that sooner rather than later. But I appreciate all the help today.
Okay.
Thanks so much,
All
Mike.
right.
Have a good weekend.
All right. You too. And I think I'll pause the video until somebody else asks a question.